Good afternoon, everyone. Welcome to Preparing Spring Web Applications for Loom. My name is Mark Thomas, and I'm a staff engineer at VMware. I'll just give you a couple of seconds to read the standard required disclaimer, and then we'll carry on. Okay, I've read it, so I'm assuming that you have as well. So, I've been a contributor to the Tomcat project for getting on for 20 years. And since August 2008, I've worked for SpringSource and then VMware with essentially a very simple job description. Go and do whatever you think is best for Apache Tomcat, which is what I get to spend the majority of my time doing. I also support VMware products that are built on top of Tomcat, particularly TC Server. But I'd probably say 90–95% of my time is Tomcat or Tomcat-related projects, both at the ASF and at Eclipse. So why are we talking about Project Loom? Well, looking at the description of Loom from the front page of their wiki, really the bit that stands out is that easy-to-use, high-throughput, lightweight concurrency. So is that actually true, essentially? How do we measure it? What does it mean for web applications? And that's what I'm going to try and dig into a little bit in this session. Before I do that, I want to set a little bit of context, and I'm going to run through a brief history of servlet scalability. We'll start back in the days of HTTP 1.0 before I was involved in Tomcat, and then go through each of the sort of significant changes there have been in scalability since then. To do that, we're going to look at a fairly simple model of a web application. So we've got a web app, it's calling to an external service, it's running on Tomcat, which has got a thread pool. Here we've got a thread pool of 30 threads represented by those letter T's. Tomcat's default thread pool is 200, but they would have just been way too small with that, so we're running this test with 30. That's all obviously running on the JVM. Those threads are what we're referring to these days as platform threads. They're effectively operating system threads with a thin Java wrapper around them. So it's the operating system that's responsible for scheduling them. So we've got the OS scheduler there, and it's got 4 CPU cores in this example to work with. We're going to be interested both in connections, so that's network connections that have been established to Tomcat that aren't actually doing anything, and requests. And a request is essentially a connection where there is an active request and response that are being processed. So what does this look like for HTTP 1.0? Nice and simple is the short answer. HTTP 1.0 was really, really easy from a developer's point of view, particularly servlet containers. You had a connection, connection was established, you allocated a thread, you used that thread to process the request and response, then you closed the connection and put the thread back in the thread pool. Really nice and simple. Not so hot from the scalability front, and also issues with latency, because establishing those connections in the first place is going to take a round trip every time, which adds significant latency. So we're doing things to improve that, which is on the next slide. But at this point, as I say, nice and simple. The maximum number of connections we can support is the same as the maximum number of concurrent requests we can support, which is essentially the thread pool size. So whatever we set the thread pool size to, that's what drives our maximum requests and maximum concurrent requests and maximum connections. So then HTTP 1.1 came along and HTTP Keep Alive. You could do Keep Alive with HTTP 1.0, but there were interoperability issues. So really, when we talk about HTTP Keep Alive, we're talking about HTTP 1.1. And here, what we're doing is we're fixing that latency issue. Now what happens is we create a connection, we send a request, we get a response back, but this time we don't close it. We keep it open, and we reuse that connection for the next request, and thereby that enables us to save that latency of the round trip to establish the connection. So brilliant, we've improved our latency. Unfortunately, we have completely, totally, and utterly destroyed our scalability. Because now, if you look at this example, we've got our 5 connections. Each one has still got a thread allocated, but only 2 of them are actually processing active requests. We've now got 5 threads out of our thread pool of 30 to process 2 concurrent requests. That's not good, and in reality, those numbers would be worse. You'd probably be lucky if 10% of your threads are actually doing something useful. So this very quickly leads to thread starvation. Essentially, the thread pool runs out of threads because they all spend their time maintaining keep alive connections and essentially doing nothing. So the way Tomcat addressed this way back when, and this is the days of Tomcat 4 and the blocking I/O connector, was okay, we'll let you use the first 75% of the thread pool, and that threshold was configurable, and we'll do keep alive with those. But once you get to using 75%, at that point, we're turning keep alive off. You're going to have to pay the latency price again, but that then does give us a thread, 25% of the thread pool will hopefully be available to process additional incoming requests. So that's how we dealt with the latency issue, sorry, the thread starvation issue, but we've still damaged our overall scalability. Now, that stayed like that until the days of Tomcat 6, so we're talking 14, 15 years ago now. And that's when the non-blocking I/O came in. And what this lets us do is we can now handle those keep alive connections in a much better way. We have one thread that manages the polar, and it's the polar's job to look after those keep alive connections, and it can monitor thousands of them on a single thread. And when there's data on one of those connections that needs to be processed, then that gets allocated to a thread from the thread pool, and that then processes it. So now what we've still got our 5 connections. 3 of them are in keep alive, but they're not using threads now. It's the polar that's looking after those. It's only the threads with active connections that are actually using, sorry, the connections with active requests that are using threads. So we're using 2 threads now. So at this point, we've now got much better scalability, and we've still got the latency improvements. And now we can maintain many, many more connections than we've got threads in our thread pool. And the Tomcat defaults, I think, back at this time was about 10,000 threads for a 200-thread thread pool. So much, much greater scalability. Maximum concurrent requests is still whatever's in the thread pool, but overall the scalability is significantly better. Now, Tomcat's actually got 2 non-blocking I/O connectors these days, NIO and the very originally named NIO2. From a functional point of view, they are exactly the same. They do exactly the same thing. The performance is barely distinguishable, but the implementations are very, very different. And really, that's why we've kept the 2. NIO2 was introduced back in Tomcat 8. The advantage this gives us is, for some users, one is slightly faster than the other. So we keep both. So if one is better for you, you can use the one that's best for you. The other advantage we have is if you hit a bug with one of the connectors, chances are switching to the other one, you've got about a 50% chance of missing the bug. Because while quite a bit of code is shared between them, quite a bit isn't. So that's another reason for keeping it around. You essentially get broadly the same performance, the same functionality, but the opportunity to skip that bug. Personally, I'd always go with NIO because the NIO2 code is so much more complicated. I'd much rather fix bugs with running on NIO than I would NIO2 any time. But they've both had bugs, and switching to the other has helped. Right, so let's skip on. And then the next change, and the impact of this change really depends a lot on your web application. This was Tomcat 7 and the introduction of the asynchronous I/O, the non-blocking I/O, and the asynchronous API. What this was aiming for was, if you have a web application that spends a lot of its time using some sort of external service, prior to Tomcat 7, your only choice was to do that with non-blocking I/O, because the only I/O the servlet spec supported was non-blocking I/O. So you had to do that call in blocking I/O. You had to do that call in a blocking way. You had no option to do it non-blocking. So if you're spending a lot of time making these calls, you had a lot of threads that were blocking that were essentially sat there doing nothing, not making the best use of your resources. So as of Tomcat 7, introduced the asynchronous API, and that lets you make calls to these external services in a non-blocking way. So now, rather than always having a thread allocated to your request and response, if you get to a point where you need to talk to an external service, you can switch to non-blocking mode. That thread gets released from the servlet request and response. It can go back into the thread pool. It can be used to do useful work on a different request and response. And then when the service call returns, then a thread can be allocated to the thread pool and processing continue. So now what we've got are our maximum connections are still way, way bigger than our maximum concurrent requests. But now our maximum concurrent requests can be bigger than the thread pool size. And how much bigger depends essentially how much time your app spends talking to external services. If it does it a lot, your current requests can be quite a lot bigger than the thread pool size. If it only does a little bit, you'll only get a little bit of an advantage. And that really brings us up today. And those changes were all in place, 10 plus years ago. And there hasn't really been that much change in terms of scalability since then. And now we have, with Java 21, virtual threads. So, as I mentioned earlier, threads we use up until now we call platform threads. They're operating system threads. They've got a thin Java wrapper around them. They have a fixed stack size, and that stack is allocated from native memory. And it has to be big enough for whatever your largest stack is in your application. Virtual threads are very different. They're completely Java. They're pure Java. They allocate their stack from the heap, and they only allocate what they need when they need it. So instantly you can see there's a possibility of making some memory savings there, possibly. Virtual threads are meant to be used for a task and then allowed to terminate. You're not meant to pull them. And so because you've got all these virtual threads, you need a way to actually, how do they actually do work? Well, the way they do work is they get attached onto a platform thread, and that's the job of the virtual thread scheduler. And as I'm sure you're all in the keynote this morning, then the virtual thread scheduler, that maintains a pool of platform threads, and by default, there's one platform thread for each core, for each processor core that's available on the machine. Now, where virtual threads really offer a lot of potential for web applications is their behavior with blocking operations. If you have a platform thread that's working and comes to a blocking operation, well, it just blocks. So it's basically sat there twiddling its thumbs, using up resources, not doing anything particularly useful until the operation completes. Virtual threads do something much, much cleverer. What a virtual thread will do is when it comes to a blocking operation, it'll say, okay, I know that's a blocking operation, but it switches and does it in a non-blocking way. At the same time, it releases the platform thread back to the scheduler, so that platform thread can go and do useful work elsewhere. The non-blocking call continues in the background. When it completes, the virtual thread becomes eligible for scheduling again, and when a platform thread's available, it will continue. So essentially what you're getting is you can write code to the blocking APIs, which are typically a lot easier to use than the non-blocking APIs. But by using virtual threads with it, you get non-blocking behavior and potentially the scalability benefits that come with that. And that really is where the significant benefits are with virtual threads. Now, do you get that increased scalability for free? Well, yes, sort of, maybe, but. And the but are it will work, but in a given set of circumstances. So there are things you might need to do a little bit of work with your web apps in order to take advantage of this. So the first thing is if you do a blocking operation inside a synchronized block, that is problematic for virtual threads because of the way the synchronized keyword is actually implemented in native code. The virtual thread can't detach itself from the platform thread. So if you have a virtual thread that enters a synchronized block and starts a blocking operation, it's effectively pinned to its platform thread, and it can't detach, it can't do the magic non-blocking, and you don't get the scalability benefits. That's a relatively simple fix, as we'll see in a minute. And it is only if you do a blocking operation inside a synchronized block. If you're just doing something like using a synchronized block to protect access to a volatile variable, that's fine. Virtual threads have no issue with that. Don't need to worry about it. It's the big synchronized blocks that have got blocking operations inside that you need to worry about. The other one is thread locals. And again, it depends how you're using the thread local, whether or not it's going to be an issue. If you're using a thread local as a way of passing some sort of current context across an API that won't let you pass that context through the API itself, that's fine. Virtual threads aren't going to have a problem with that. However, if, like Tomcat, you're using them as a form of thread-safe cache, then that's potentially problematic. Because with a platform thread, first time the platform thread hits that piece of code, okay, it initializes the thread local, it creates whatever object it is you want to cache, puts it into the thread local, and then it uses it. Platform thread goes back into the pool, gets taken out for another request, reuses the object in thread local cache and goes round and round and round again, and it's always got that object in the thread local cache. Virtual threads, because they're not pulled and they're not reused, what happens is the first time round, okay, create the thread local, create the object, put it in the thread local, use it, terminate. Next virtual thread comes along, create the thread local, create the object, put it in the thread local, use it, terminate. We're not getting the benefit of reusing those objects. We're having to recreate it every single time. So haven't really got a cache there at all. All we've actually got is a bunch of extra overhead that if we're only using the object once, isn't actually helping us at all. If we use it several times, we'll probably get some benefit. But if we just use it once, not helpful. So that's another area where you won't necessarily have a problem, but the performance might not be quite what you are expecting. So if we look at our little web application example with virtual threads, then things do look a little bit different. Our thread pool is a lot smaller. We've now only got one platform thread per processor core, so we've got 4. We've now got this added scheduler, the virtual thread scheduler, and it's responsible for mapping those virtual threads to our platform threads. And this raises all sorts of interesting questions. If I switch to virtual threads, what does that do to throughput? Are virtual threads faster than platform threads? Slower than platform threads? About the same? Now, my guess is they're about the same, because you have to mount a virtual thread on a platform thread to actually do work, and you then expect the platform thread to execute as quickly as it would normally. So, yeah, they should be about the same, but what about the overhead of all of that mounting, scheduling? Is that worse or better? Don't know. That's one of the questions we want to answer. What's our impact on scalability? Well, virtual threads are definitely lighter weight. So we should be able to have more of them with the same set of resources, which potentially lets us have better scalability. But virtual threads are not a magic create extra CPU power out of nowhere feature. If you're already CPU bound, switching to virtual threads isn't magically going to create some extra CPU. So it depends what your limits are on your scalability. But if it's not CPU, and say it's memory, then virtual threads might be able to help you get greater scalability. What about GC? Remember I said that virtual threads allocated their stack in the heap. That means you can have extra churn in your heap, so the GC is going to have to work harder to clear it up. Okay, so we might have a little bit more GC pauses, but we're going to have a smaller memory footprint because we don't need to allocate the maximum stack size we need for all of our threads in native memory all the time. We just allocate the stack we need in the heap, so we can save a bit of memory footprint. So there's some interesting things there, and that's before you remember that throughput, GC pauses, and heap size are interrelated anyway. You can optimize any two of those at the cost of the third. So you can have not high throughput, low GC pauses, but the price you pay is a much larger heap. Last time I checked, the recommendation was about 2 to 3 times what you needed in steady state. So significantly more heap to get those benefits. If memory's a resource you're restricted on, okay, you bring the memory down, that's fine, but you're going to have to pay the price in terms of throughput or longer GC pauses. So there's some trade-offs there. These things aren't as independent as we perhaps might like them to be. Then there's that extra scheduler. So let's ignore virtual threads for a minute. We've got our Tomcat instance. It's running with the defaults. We've got 200 platform threads. It's reasonably busy. It's the only thing running on this particular machine. So the CPU, the OS scheduler is going to allocate pretty much all of the CPU to those 200 threads. There's a little bit that it will allocate for background OS stuff, but the majority is going to go to the 200 platform threads. Okay. Switch to virtual threads. Now we haven't got 200 quite busy threads. We've got 4 very busy platform threads. Does that change how the OS scheduler behaves? Probably. Does it change the end result? Probably not. But there are interesting things going on there with, well, yeah, but you don't have to do context switching as much because you've only got 4 platform threads that are really doing all the work. And you've got 4 cores, 1 thread a core, great, happy days, no need to context switch. So you might get some benefits there. So there's going to be interesting things going on at a fairly low level. Okay, keep that in mind. Now think of a slightly different scenario. for whatever reason, you're not running Tomcat on its own. There's Tomcat that's got 200 platform threads and some other process that's got, say, 200 threads. Let's keep it simple. Okay, assuming they're equally busy, equal amounts of work to do, the OS scheduler is going to give them roughly 50% each of the available CPU. Now switch Tomcat to virtual threads. Tomcat is now showing 4 very busy platform threads, and the other process is still showing 200 quite busy platform threads. Is the OS scheduler still going to split the load 50-50, roughly? Probably. Maybe not. Maybe there are some slight differences. So that's going to get interesting. You're still going to get context switching, because now you've still got more threads than active threads than you've got cores. So you're going to see slightly different effects in that case. And let's not forget that this is VMware Explore, so you're not going to be using bare metal machines for this. It's all going to be virtualized, isn't it? And so you haven't just got the OS scheduler and the virtual thread scheduler. All of this is running on a hypervisor, and it's got its own scheduler that's mapping all of that to the real cores underneath that. And how all of these are going to interact, is it going to be exactly the same if you run your Tomcat load on platform threads? Exactly the same as virtual threads? I suspect not. They'll be pretty similar, probably, but how different they'll be and how much those differences matter is really going to depend on your application, your requirements, your circumstances. It's definitely the sort of thing you're going to need to test in your environment and see how it behaves. But just keep in mind that there are these differences and it might change the underlying behavior. Right, now I need to move on because I always talk for far too long with that slide. So, lots of things to look at. What I wanted to try and do was pick out a number of them, try and look at them independently as best I can, and give you an idea of, well, what's the impact of this? And if you want to go and look at it in your environment, what sort of things do you need to test? How could you start looking at it? So, let's start with throughput. Now here, I really wanted to answer that question. Okay, are virtual threads faster or not than platform threads? Now, I'm really interested in the relative speeds, relative performances of the two. So I'm trying to eliminate things like, well, if we're CPU bound, virtual threads and platform threads might behave differently under that scenario. So I'm trying to avoid being CPU bound, so the concurrencies are actually fairly low. And we'll see when we do become CPU bound at the top end, we do start to see some additional differences. So we looked at some different sized requests, different concurrencies. I tweaked Tomcat to minimize sort of the time Tomcat spent doing Tomcat stuff. So we had lots of keep alive. We turned off access logging because that's relatively large overhead. And I was trying to reduce the overhead to try and maximize the difference between platform threads and virtual threads on the assumption that the difference was going to be fairly small. So the more I can eliminate overhead, the easier it's going to be to see that difference. Cut a long story short, those are the results. Each color represents a different sized request. Unsurprisingly, different sized response. The smaller the response, the higher the throughput. Well, that's not a surprise because we spend less time writing to the network, more time processing the request. So that's sort of what you expect. And for each color, there should be 2 lines. There's one with a little diamond on it, which is the virtual threads, and one with little crosses on it, which is the platform threads. And generally, the virtual threads are ever so slightly higher in terms of throughput than the platform threads. And as the response size gets smaller, so we spend less time writing to the response and more time processing more and more requests, those differences become more stark. So yes, virtual threads are a little bit faster than platform threads. The difference that I measured was about 30 microseconds. That's micro, not milli, so 30 millionths of a second. And that may or may not be significant for you. Depends on your particular requirements. But it's not all, there are costs associated with that slightly higher throughput that I'll talk about in a minute. Other things that are worth noting, interestingly for platform threads, if you have a concurrency of 2, the throughput actually goes down, which was a bit of a surprise. And digging into that, it's all to do with locking in the thread pool. It just spends more time, just getting the threads in and out, it was spending more time doing that. Once the concurrency went up, that sort of effect went away a bit. And you'll see on the far right, particularly at the top, the lines start to separate. And that's the impact of becoming CPU bound. We haven't got the full results here, but some informal testing I did indicated once you become CPU bound, initially virtual threads handle that situation a little bit better. But once you increase the concurrency even more and put even more load on it, actually they come back together again. So if you're just slightly or at the limits of your CPU, then virtual threads tend to be a bit better. But once you go a long way over, then there's not that much difference between them. And why do we get that 30 microsecond difference? It comes back to how we manage the queues of work that we've got to do. Platform threads, Tomcat standard thread pool uses a link blocking DQ. That's a fair queue for the tasks that need to be processed. But because it's a fair queue, first in, first out, to ensure that fairness, it uses a little bit of locking. And that locking comes at a price, and the price is about 30 microseconds. The virtual threads, they use a work stealing queue, which doesn't have that locking, so it's that little bit faster, but it's also not fair. So it's possible that things get processed out of order, which will have an impact on your latencies. And my colleague Violetta did some tests on this, not quite as well documented as the previous lot, but all credit to her. If there's anything wrong with this, definitely my fault. But in summary, she did a test with much higher concurrency, multiple machines running in the cloud. And with the test she did with platform threads, she got about 3.37 million requests, but they all completed within 800 milliseconds. Exactly the same system, just switched it to virtual threads. We got the higher throughput, about 3.41 million requests, so about an extra 1%, just over. But because of the work stealing queue and things being slightly out of order, we had the impact on latencies. So now only 89% of our requests completed within 800 milliseconds. 9% of them took between 800 and 1200, and 2% took over 1200 milliseconds. So yes, overall, our throughput has gone up, which is good. But the price we've paid for that is some of our requests have taken a little bit longer. Now, that's a trade-off that some people will be quite happy with. Other people say, absolutely no way, don't want it. I'll take the more consistent latencies. So again, and that's another thing you need to look at quite carefully if you're looking at using virtual threads in your app. Now, what about easy to use? What I've got here is the code you need to write if you use the servlet blocking I/O API, just to count the number of bytes in the request body. Don't worry if you can't read the code. That means you can't see my mistakes, but the actual code isn't the important bit, it's the volumes that matter. Because if I write that same code using the non-blocking API, it looks like that. Whoops, wrong way. Try that again. Like that. A lot more code. It's more complicated, it's harder to write, it's easier to get wrong, and that's not actually complete. I've skipped some of the error handling, because error handling with non-blocking and async gets really nasty because you have a whole bunch of race conditions you have to handle. Things like what happens if a timeout fires, but between the timeout firing and it actually getting to your application, the non-blocking operation you're waiting for actually returns. And which one wins? Do I ignore the timeout? Do I ignore the return? Complicated. Now, some of that complication Tomcat has to deal with. Some of it the application has to deal with, but it's a lot more complicated. Let's call it, in this example, it's about 4 times as much. So the question is, given all of that, if I write the blocking I/O example and use virtual threads, how does that perform compared to the non-blocking I/O example with platform threads? So the question I'm trying to ask is, if I've got a blocking I/O and I switch to virtual threads, is that a quick way of effectively rewriting my app using non-blocking I/O? And the short answer is yes, given those latency concerns we talked about a couple of slides ago. Generally, what we did here was I essentially faked an external service that blocked. Initially, what I found was whatever delay I put on that block, that dominated the results. So I ended up reducing it down to 0. So there wasn't actually any delay, but it still went through all the overhead of doing the blocking or doing the non-blocking. So the overhead was all there, and it's the overhead we really wanted to compare. And the overhead between the two is virtual threads comes out slightly ahead. Again, at very low concurrency, we see issues with locking in the thread pool. And again, when we get to 32 threads, because on this machine it had 20 cores, we've got that little bit of CPU-bound contention. So again, virtual threads start to look a little bit better. Next thing I wanted to look at was coding constraints. So issues with virtual threads and pinning. If we want to avoid those blocking operations in our synchronized blocks, there's a quick way to detect them. Java 21 provides an option, JDK trace pin threads. You can either get a full stack trace or a short one. For me, the short one's always been fine. I've never had to use the full, but your mileage may vary. Don't particularly like that it logs it to standard out, but I'm probably only going to use this in dev, so I can live with that. I don't think this is something I'd want to turn on in production. And in Tomcat, it works really well. We had a report on the users list that our H2 implementation was doing a lot of pinning. So it's a simple solution to that. Let's turn on this option in our CI system, switch the CI system to using virtual threads, and see what happens. What happened was about 1,000 error reports across all of the tests. Fortunately, a lot of them were repetitive. There's actually only about 20 errors there. Went through, fixed them, and essentially it's all a case of just replace a synchronized block with a reentrant lock. Now, that's fairly simple. There's just two things you need to keep an eye on. First of all, make sure you release the lock. There's a standard pattern for that, so that's not actually that hard as long as you follow the pattern. The slightly harder bit is you've got to make sure you replace all of the synchronized blocks on that object with the reentrant lock. Otherwise, bad things happen. And for Tomcat, that was a little bit tricky because the H2 implementation isn't perhaps as clean as I would like it to be. Yeah, my fault, I wrote it. But some of the objects are locked across multiple classes. So it took a little bit of effort just to make sure that we got all of those synchronized blocks replaced in the right places. But otherwise, it's just a standard replace a synchronized block with a standard lock pattern, nice and simple. Thread local alternatives. As I said earlier, Tomcat uses thread locals for various caches. Regular expressions in the rewrite valve, but the one I'm going to focus on is in the request dispatcher, where the object that restores the results of the mapping is actually fairly heavyweight, and we don't want to recreate it every time, so it's put in a thread local cache. And really, we've got three options. We can carry on using the thread local cache, we can ditch the thread local and just create a new object every time, or we can use one of Tomcat's other caching options, and we have several. Synchronized stack was the one I chose for this. Now, my expectation was that thread local would always be better with platform threads than virtual threads. New object would always be better in virtual threads than platform threads, and synchronized stack would always be better than both of them. I was completely, totally, and utterly wrong. So again, yeah, trying to guess performance behavior without actually testing it never seems to work. Why is that? Well, if you always use new object, you lose the benefit of the caching. Okay, so you think performance should be worse. But a lot of those caches date back quite a long time and were more to do with reducing GC churn than they were raw performance. And the GC's got a lot better since those caches were introduced. So do we actually need them or not? Perhaps not. But what we ended up doing, or what I ended up doing was, wrong way again. That's better. Series of tests, different concurrencies, each of the three options, virtual threads, platform threads, took all of the possible combinations, ran 11 tests for a minute, ignored the first one because I treated it as a warm-up, take the average of the remaining 10, hopefully trying to get the variation between the results to a point where I could actually see differences. And no, there was no clear winner or loser with any of them. So in the end, I said, fine, I'm not going to try looking into this anymore. I'll leave it as is, and we'll wait to see if any Tomcat users report issues in particular scenarios. Then we'll look at those scenarios and see what we need to do to fix those. That, I think, is, given these results, that's going to be much more productive than trying to guess the best way to optimize code. Because as I say, that as an approach never works. So in conclusion, if your application is already using your non-blocking framework of choice, whether it's servlet async, whether it's reactive, whether it's something else, then you're unlikely to see much difference either in scalability or throughput if you switch to virtual threads. If, however, you're currently using blocking APIs, then if you switch to virtual threads, you won't see much difference in throughput. Remember, you might see a bit of difference in latency, but where you'll potentially see benefit, if you do the refactoring to deal with the synchronized blocks and the thread locals, is in scalability. And that's where the real potential benefit of virtual threads is, in my view. So where do we go from here? Well, Tomcat now has virtual thread support. It's as simple as use virtual threads equals true on any connector. It's available in all of the current Tomcat versions. Obviously, Tomcat 11, you're going to need to use Java 21 because it has a minimum of Java 21. The others, if you want to use virtual threads, yes, you've got to use Java 21, but their minimum versions stay the same. In terms of future Tomcat development, at this point, I think we've done all we're planning on doing. We're not going to, do any more performance tests. We don't think we need to do anything else to get Tomcat to be virtual thread ready. So it's there, and we're essentially waiting for feedback to users to tell us, actually, you're wrong, need to fix this bit, and we will. And Tomcat, if you're not already aware, has monthly release cycles, and we aim, and we pretty much stick to it, of fixing all open bugs that we can recreate for the next release. And I mentioned that caveat because there's a few that have lasted for 6 months or more because we couldn't recreate them. But the ones that we recreate, and to be honest, most of them we can, they will get fixed to the next release. So if you find a problem sometime in the middle of the month, first week of the next month, that you should have a Tomcat release with the fix. So at this point, I've got a couple of minutes for any questions. Yes? Okay, so the question is, what's the planned default for virtual threads? At the moment, Tomcat has no plans to change it from the current default, which is a platform-based thread pool of 200 threads. It's too early, I think, to think about changing it, but we'll react to the user community. If the user community in a year's time says, look, we're all using virtual threads, they're brilliant, they're amazing, why would anybody use platform threads? Yeah, we'll look at it and we'll probably change it. But that, I think, is very much going to be user community driven. Yes?
Do you know if they plan on having a way to, Project Loom question, a way to switch to FIFO fair?
I don't know a definitive answer. I have seen at various points in sort of the various Loom papers, the option discussed of having the scheduler being pluggable so you can put your own in. What I can't remember is whether that was a suggestion that got tried and rejected or never implemented or is actually there. But it's one of those. But it was discussed. But if you do that, I think where you're going to end up is the throughput's going to be pretty much identical. The latencies will be the same, but you get that way you get the scalability benefits. So yeah, if it's, I'd be surprised if it wasn't going to be possible at some point, but I don't know the definitive answer to you now. But we can always have a look afterwards if you like. Any other questions? Okay, I've only got a minute left, and I want to finish on time. So. If you do think of any questions between now and tomorrow afternoon, I'll be at the Ask the Expert bar in the hub at 3:30 for an hour and a half. So any Tomcat or TC Server related questions, feel free to come along and ask. If that time doesn't work for you, feel free to reach out to me at my Apache email address anytime this week. My diary, apart from tomorrow, is largely empty. And I'd like nothing more than to sit and chat about anything Tomcat related. So if you or any colleagues have got Tomcat questions, drop me an email. We can set up a time. Happy to talk about it. After this week, then there's obviously always the Tomcat mailing lists. feel free to post your questions there. And with 10 seconds left, please remember to take the survey, and thank you very much.